Welcome to our module on neural networks and deep learning, a fascinating and rapidly evolving field in artificial intelligence. Today, we'll explore the foundational concepts and delve into advanced architectures that drive modern AI applications. Let's begin with perceptrons, the very simplest form of a neural network, a crucial starting point. Perceptrons serve as fundamental building blocks, primarily designed for basic binary classification tasks. First, let's establish a clear definition of what a perceptron actually is within our context. A perceptron is the most basic artificial neural network, specifically designed to handle binary classification problems. Next, we have the input layer, which is where all our data initially enters the network. This layer is responsible for receiving the raw input features that are essential for the network's processing. Crucially, each input feature is associated with a weight, and a bias term is also incorporated. Each input feature is multiplied by its unique weight, and then a bias term is added to this cumulative sum. Following this, the activation function determines the perceptron's final output based on the processed input. It's a step function that converts the weighted sum into a binary output, either 0 or 1. Finally, the primary training objective is to refine the network's parameters for accurate predictions. Our goal is to iteratively adjust these weights and the bias to minimize any prediction errors encountered. Now, let's explore the mathematical formulations behind the perceptron's output and how its weights are updated. These mathematical foundations are essential for understanding how binary classification is performed and learned. First, let's look at the formula that defines the perceptron's output, determining its classification decision. The output, denoted as y, is 1 if the sum of wi times xi plus b is greater than 0, otherwise it's 0. Here, y represents the final output of our perceptron, which will be either 0 or 1. Wi is the weight assigned to each individual input feature xi, influencing its importance, and xi refers to the specific input feature value that the perceptron receives. Finally, b is the bias term, an additional constant that shifts the activation function's output. This formula effectively describes how the perceptron calculates its decision based on the inputs. The perceptron will output a value of 1 if the weighted sum of inputs, along with the bias, is positive. Conversely, if that sum is not positive, the perceptron will then output a value of 0. Next, let's delve into the weight update rule, which is how the perceptron learns from its mistakes. The updated weight wi is the old wi plus eta times the difference between y true and y pred, multiplied by xi. Here, wi refers to the specific weight that is currently undergoing an adjustment during training. Eta, or $eta$, is the learning rate, a crucial parameter that controls the step size of our updates. Y true represents the actual, correct label for the given input data point, while y pred is the label that our perceptron has predicted for that same input. And xi is the corresponding input feature that contributed to the prediction. This rule forms the core of the perceptron learning algorithm, enabling it to learn effectively. The weights are adjusted in proportion to the prediction error and the associated input feature. This iterative process systematically reduces the discrepancies between predicted and actual labels, improving accuracy. Moving beyond single perceptrons, we now explore multilayer perceptrons, their structure, and key activation functions. MLPs are powerful, enabling the modeling of complex relationships and nonlinear classification tasks effectively. Let's break down the essential components that make up the structure of a multilayer perceptron. The input layer is where the network receives the raw input features, just like in a single perceptron. Hidden layers are intermediate layers of neurons, each with its own activation function, situated between input and output. The output layer is the final layer that produces the network's ultimate prediction or classification result. Crucially, MLPs are capable of modeling highly complex, nonlinear relationships within data. Now, let's look at some of the key activation functions that are vital for MLP functionality. The sigmoid function, defined as 1 divided by 1 plus e to the power of negative x, outputs values between 0 and 1, ideal for binary classification. ReLU, the rectified linear unit, outputs the maximum of 0 and x, values greater than 0, widely used in hidden layers. The tan function, which is e to the x minus e to the negative x divided by e to the x plus e to the negative x, outputs values between -1 and 1, suitable for various tasks. These functions introduce nonlinearity, which is essential for MLPs to effectively learn and represent complex patterns. Today, we'll unravel the mystery of backpropagation, the fundamental learning algorithm that powers most neural networks. First, in the forward pass, input data moves through the network, generating an output prediction. Next, we calculate the loss, which quantifies the difference between our network's prediction and the actual target. Then, during the backward pass, we propagate this calculated loss backward through the network to determine gradients. Finally, using these gradients, we update the network's weights and biases to reduce the overall loss in future predictions. Now, let's explore optimization algorithms, crucial for training neural networks efficiently and effectively. These algorithms focus on adjusting network weights to minimize the loss function as effectively as possible. Starting with batch gradient descent, it's an optimization method that considers the entire dataset. Specifically, it computes gradients by using every single example from the complete training dataset. While providing stable convergence, this method can be quite slow, especially with very large datasets. Next, we have stochastic gradient descent, a faster approach for updating network parameters. Here, gradients are computed using only one single training example per iteration, making it very quick. It offers faster training, but the weight updates can be noisy and fluctuate due to single example gradients. Minibatch gradient descent strikes a balance, using a small subset of data for updates. It computes gradients using a small subset, or minibatch, of the training data in each step. This method effectively balances the training efficiency of SGD with the convergent stability of batch gradient descent. Beyond these, we have advanced optimizers that further enhance the training process. Momentum accelerates convergence by incorporating a fraction of the previous weight updates, smoothing the path. Atom adapts learning rates for each parameter individually, using estimates of both first and second gradient moments. Let's dive into the core components that make convolutional neural networks so powerful for image processing. These are the essential building blocks specifically designed for processing image and other visual data. Convolutional layers apply learnable filters to input data, creating feature maps that detect patterns. They apply these filters across the input, generating feature maps that highlight specific patterns and edges. Activation functions like ReLU introduce crucial nonlinearity, allowing the network to learn complex features. They introduce nonlinearity, for example, ReLU, enabling the network to grasp more intricate and complex features. Pooling layers reduce the spatial dimensions of feature maps, making the network more robust. These layers reduce the spatial dimensions of feature maps, helping the network become robust to minor shifts. Fully connected layers are traditional neural network layers that make the final predictions. These traditional layers take the extracted features and use them to make the final classification or regression predictions. Normalization techniques, such as batch normalization, stabilize training and improve model convergence. Techniques like batch normalization help stabilize the training process and significantly improve convergence speed. Now, let's explore processing sequential data, from recurrent neural networks to long short-term memory networks. This section focuses on how we handle temporal dependencies and the challenge of long-term memory in sequences. Recurrent neural networks, or RNNs, are designed to process sequences by maintaining an internal state. However, RNNs often suffer from vanishing or exploding gradients, making long-term dependency learning difficult. This challenge led to long short-term memory networks, or LSTMs, a more advanced architecture. LSTMs use specialized gates for get, input, and output to control information flow within the cell state. The cell state update logic allows LSTMS to selectively remember or forget information over long sequences. Alright class, let's wrap up our discussion on neural networks with a quick summary of what we've learned today. Here are the most important key takeaways that you should definitely remember from our deep dive into neural networks. First, remember that perceptrons are fundamental single-layer networks, primarily used for straightforward binary classification tasks. Multilayer perceptrons, or MLPS, utilize hidden layers and activation functions to effectively model complex, non-linear relationships in data. Backpropagation is crucial. It's the core algorithm for training neural networks by carefully adjusting weights based on calculated gradients. Remember, optimization algorithms such as gradient descent, momentum, and ADAM are key to guiding efficient weight updates during training. Convolutional neural networks, or CNNs, truly excel in image processing, leveraging convolutional and pooling layers for robust feature extraction. Finally, RNNs and LSTMS are perfect for sequential data, with LSTMS specifically designed to handle long-term dependencies and gradient issues.